In this video, we're looking at a small piezo micromotion stack. Piezoelectric crystals, when you apply a voltage to it, it will move. In this case, we have a signal generator up here. We're applying a small AC voltage to this crystal and it's causing it to oscillate. We have the frequency set to 100 Hertz, which we can see on the scope here. This is our AC output from the MTI 2100. Our probe is fixtured right here. I've previously fixtured the probe and calibrated it. Exciting the crystal at 100 Hertz at about 400 millivolts, and that's giving us 25 microns peak-to-peak motion here. We also have a spectrum analyzer, which we'll look at in a minute, so we can see what the signal looks like in the frequency domain. This is the time domain image right here on this oscilloscope. And what we want to do here is we're going to turn down the amplitude of the voltage such that we can get down to about 1 to 2 nanometers of peak-to-peak motion. So you can see that it is possible to resolve very small motion with the photonic sensor. So what we're going to do is we're going to drop our amplitude down such that we see about 1 nanometer of motion here. We do that by reducing the peak-to-peak voltage. Increase the sensitivity of our scope, and we have about 36 millivolts peak-to-peak exciting the crystal. In the time domain, we can start to see the bass noise floor of the instrument, and we're almost losing our signal here. It's so low. You can increase the amplitude a little bit more, and you can see if you have any seismic motion, you're also going to pick that up. The meter resolution on the 2100 is right down at the bottom level now. We're only showing about 1 nanometer of motion. However, on the spectrum analyzer, we can more easily pick this sinusoidal motion out. Because it's sinusoidal in nature, it has a frequency component that's easily identified in the frequency spectrum. And one of the things we wanted to point out today is that using this spectrum analyzer, you can increase the sensitivity of this instrument. It's an analog instrument, so there's no quantization or digitizing of the output, and it goes right down to angstroms of resolution. So although we really can't read the peak-to-peak motion here anymore, we can see it on the scope, and I can see over here that I have about 1.5 millivolts RMS peak-to-peak signal. So it's quite readily visible in the frequency domain. So a spectrum analyzer, which could look at signals, sinusoidal signals or repetitive signals in the frequency domain, is a useful tool to use with a photonic analyzer. It actually enhances the resolution of this tool by at least another factor of 10, perhaps 20 times, getting down to angstroms of resolution. We can see here we have our lower frequency set to 10 Hertz and the upper one at 210. This is exactly at 100 Hertz. So by moving the cursor here, we can look at the peak, and we can see that the signal-to-noise ratio is still is very, very good in the frequency domain. All right, our 2032 module is in high resolution mode right now, and the sensitivity factor is 0.5 nanometers per millivolt. Over on the scope here, we can see about a little less than 10 millivolts peak-to-peak of signal, which would be about 2.5 nanometers, somewhere in the range of 2 to 2.5 nanometers peak-to-peak of motion. On our spectrum analyzer, we're seeing about 2.4 millivolts RMS. So if we convert RMS to peak-to-peak times 5, that's given us about, it's about 5 millivolts peak-to-peak. And that's working out to about 2.5 nanometers of signal here, of motion. So this thing's actually oscillating up and down at about 2.5 nanometers. And if we take a look at in the frequency domain here, we have quite a strong signal peak showing that motion. And we can actually get down to a resolution of probably 1 angstrom of motion. We can easily drop this by a factor of 10 and still be able to see that signal before it hit the noise floor. So it's quite an impressive instrument in terms of picking up very, very small motions. And we use the piezoelectric crystal because it's capable of producing such small sinusoidal motions with a That's easily controlled by a signal generator here.